Hello. In this video, we'll be talking about topic 3.5 of the AP Chemistry curriculum, Kinetic Molecular Theory. And specifically, we'll be talking about gases here. So with kinetic molecular theory is just a list of postulates about how gas particles behave. And so I'm going to go through the six statements of the kinetic molecular theory and just describe them briefly. So the first one is gas particles are very small particles, relatively speaking, with mass. In other words, they are not massless. They have mass, and this means that gases actually do have mass. If you filled up a balloon with air, the balloon with the air in it will weigh more than the balloon without the air. If you fill up a balloon with helium, the balloon with helium is going to weigh more than the balloon without the helium. So the particles are very small in a gas, and they have mass. Second statement of the KMT is that there is a relatively large distance between the particles. And what this means is that the particles are very, very far apart relative to their size. Now, this is important because with ideal gases, we say that the particle size doesn't affect the volume of the gas. And I want you to think about this. Let's say that we had a container and we have 5 particles of gas in there. 1, 2, 3, 4, 5. Notice that those particles are very small and most of the container is empty space. So the particle size is very small compared to the volume of the space. So therefore we can say that the particles themselves have no volume because the space itself is so big. But if we took this into a very small little container and I drew those same 5 dots, 1, 2, 3, 4, 5, those particles' volume now does matter. And so when we talk about gases, we're often talking about large volumes where the particles' volume doesn't matter. And so with ideal gases, we typically say the particles have 0 volume. But in a small container under high pressure, the particles' volume does come into account. So just keep that in mind when we talk about this particular statement of the kinetic molecular theory. Number 3, the particles are in constant random motion. So the particles are moving around in random motion, bouncing off the walls, bouncing off each other, and they are in constant motion without losing any kinetic energy. Which brings us to this part. They are perfectly elastic collisions. And if you have not taken physics, what perfectly elastic means is that they bounce off each other without losing any of their without losing any total kinetic energy. So a particle may slow down after hitting another particle or hitting the wall, but it is going to give that extra kinetic energy to the other particles. So the particles overall are staying the same overall kinetic energy. What do I mean by kinetic energy? Well, kinetic energy is moving energy, and we can calculate the kinetic energy of a particle by multiplying 1/2 times the mass of the particle times the velocity, the speed of the particle squared. So kinetic energy can be calculated by knowing the mass of the particle and how fast the particle is moving. That's how we can calculate kinetic energy. So what is a measure of kinetic energy? Well, temperature is. And so average kinetic energy of the particles only depends on temperature. Doesn't depend on volume, doesn't depend on pressure. It only depends on temperature. Now, if the pressure and volume change, you can change the temperature, but the temperature itself is what is a measure of the average kinetic energy. Now, notice the key word here is average. Some particles are moving faster and have higher kinetic energy. Some particles are moving slower and have lower kinetic energy. But on average, when we talk about the kinetic energy average, that is proportional to the temperature of the gas in Kelvin. Why in Kelvin? Because if there is no velocity, how much kinetic energy do you have? No kinetic energy. And if you have no kinetic energy, you have no temperature. And the only scale that has no temperature at 0 kinetic energy is Kelvin. So that's why we have to use Kelvin in all our gas laws, is because 0 on the Kelvin scale corresponds to 0 kinetic energy. And in our 6th statement in the kinetic molecular theory is there's no force of attraction or repulsion between the particles. So no forces between the particles of the gas. Now, of course, you know that particles do have polarity to them, or they can have momentary dipoles, meaning that they can attract each other. And so, again, this is for an ideal gas, but real gases do attract each other slightly, some more than others. But for ideal gases, there's no force of attraction. And if the particles are very far away from each other and moving very fast, have a high temperature, that force of attraction is negligible. So these are the 6 postulates or the 6 statements of the kinetic molecular theory, which all have consequences, of course. One last thing I want to show you is just a graph called the Maxwell-Boltzmann distribution. And what I have here is a graph of helium, neon, argon, and xenon, all at the same temperature. So these are all at the same temperature. Notice that xenon, which is this light purple here, we have kind of a Barney purple here, on average, which is the peak of this graph, on average has the lowest speed. I have speed on the x-axis, and xenon particles are moving the slowest. What this graph means is some particles are moving slower, some particles are moving faster. Most of the highest number of particles, which is this peak, which is a probability density, the highest number of particles are moving with this velocity right here, 200 meters per second. Some particles are moving faster, some are moving slower, because again, on average, they have a certain kinetic energy. So some might be moving slower, but that averages out with the ones that are moving faster. So this peak represents the largest number of particles and the average speed and therefore kinetic energy of these particles. If you look at the blue one, argon, the average is a higher speed, somewhere right about there, which is about 380 or so, 350, somewhere in there. But they're moving faster on average. If you look at neon, those particles are moving even faster at this temperature. They're moving at 500 meters per second. And if you look at helium, on average, they are moving the fastest at 1100 meters per second. So why would helium atoms be moving faster than xenon atoms if they're at the same temperature? Because we said temperature is the average kinetic energy. So if they all have the same temperature, they all have the same kinetic energy. So the kinetic energy of each of these particles on average is equal to one another. But remember, kinetic energy is 1/2 mv squared. So if we have a small mass, then we need to have a big velocity to give it the same kinetic energy of something with a big mass and a small velocity. In order for a gas to have the same kinetic energy, a small gas has to move faster and a large gas has to move slower to have the same kinetic energy. So at the same temperature, big mass gases travel slowly and small mass gases travel quickly so that they have the same kinetic energy at the same temperature. So helium with a mass of 4 is going to travel much faster than xenon with an average mass of 132. The reason that these are spread out more is because if a gas is capable of moving faster, then it can have more possibilities of speeds. And so helium with the highest average speed is going to have a larger distribution of speeds than a gas with a slower speed. It's going to have a smaller distribution width of this graph because particles can't move a whole lot faster. And of course, you can only go down to 0 movement. So the distribution is going to be smaller. So heavy gases have small distributions and low speeds. Light gases have high distributions and high speeds. So that's where I'm going to stop for today. If you have any questions about this, please let me know.